us that there is an action related to the libraries of the universities, because you know that the change in the government regulations imposed that starting from the 5th of November, the in-class teaching will be allowed only for the students that belong to the first year. And laboratories and all the remaining teaching activities. Okay, so in your case, for this class, there is no change because it is already fully in remote. But the important information is related to the libraries, because from November 5th, all library services to the public have been suspended. And for this reason, the university is putting in place solutions trying to fix this inconvenience of the impossibility for the students to enter the libraries. Essentially, what they want to do is to make more than 2,000 ebooks available online for the users of the library by the end of November. And what they say is that the books have been chosen among those that are most requested by users. So, and that are signaled as required in the examination programs of the teaching staff of the University of Bologna. So I will check whether the text that I am using for parts of this class is among those of that will be made available to the students. Another issue is that a few months ago, due to the beginning of the pandemic, I received a message from the publisher Springer saying that they had selected 500 titles of books that had become available for free in electronic form on the web. And among these books, there is the first edition of my book that is entitled Physics of Semiconductor Devices. And this is also one of the texts that I'm using for this class. So now, at the time of the first pandemic, the availability of these books to be downloaded was from March to end of July. I do not know whether the term has been extended, but probably or possibly it has been extended or will be extended. So my suggestion is to check. It's easily done in internet. You check free download from Springer, okay? Just to check whether this possibility is still open, okay? In that case, you may download the first edition of the book in which much of the material of the second edition is already present, okay? And you may exploit some of this material for the as notes for this class. Okay, and also check whether the university libraries check the lists of the books that have been made available by the university libraries. Okay, so this is it for the information. Now we go back to the topic that we were discussing at the end of the last lesson, that was the piezoelectric effect. You may remember that at some point we started with the surfaces of equal energy. Sorry, but as usual, sharing the screen is not so easy sometimes. So let's go away with this. Okay, you should be able now to see the surfaces of equal energy of the conduction band of silicon, germanium and gallium arsenide. We are interested in silicon, and these surfaces are the ellipsoids of rotation that are the total 6, and they are grouped in 3 groups of 2 ellipsoids. One group is aligned with the 1, 0, 0 axis. The other one is aligned with the 0, 1, 0 axis, and the third one with the 0, 0, 1 axis. You remember that we are in the K space, but the unit vectors of the K space for silicon coincide with the coordinate axis. Okay, so 1, 0, 0 is also the x-axis in the direct space. 0, 1, 0 is the y-axis, and 0, 0, 1 is the z-axis. Now, assume that you will cut this figure using a horizontal plane that coincides with the 1, 0, 0 and 0, 1, 0 axis. Okay, so after this cut, you can see a 2-dimensional figure that we are going to see next, in which the section of these ellipsoids will become visible. So you will see ellipses, okay, on the XY plane essentially. So we now change we are here. So change again the view. And now you should be able to see this section. The axes in this figure are called PX, PY, because you remember in the K space, you have Kx, Ky that also are equivalent to K1 and K2, but if you multiply K by H bar, you obtain the average momentum of the electron, so that the symbols here are P because they are reminiscent of momentum. Now, if there is no mechanical stress, the sections of the ellipsoids are identical to each other. So in absence of stress, the section of the ellipsoids are the continuous line. So I'm marking them with the mouse. So this is along the x-axis on the right-hand side, and this is on the x-axis on the left. And then the continuous line here, of course, it is rotated with respect to the other axis, but the ellipsis is the same. And similarly, if you look below, this other ellipsis is the same, okay? In absence of mechanical stress, and in the condition of equilibrium, or also in a condition near equilibrium, the population of the electrons of the conduction band is equally distributed over the 6 ellipsoids. Okay, the 6 minima of the conduction band. Population is equal. Okay, so the concentration of the electrons in near each minimum is 1/6 of the total concentration. And this applies in the equilibrium condition rigorously, and also approximately in a non-equilibrium condition that is not too far from equilibrium. Now, assume that we are in a non-equilibrium condition, and also assume that the material is uniform and that an electric field is applied in the vertical direction. Okay, so you remember the electrons react to the application of an external force with an inertia that is determined by the transport effective mass. And this transport effective mass is substantially an average, like the inverse transport effective mass is a weighted average of the transversal and the longitudinal masses that are associated to each ellipsoid. Now, if you look in the figure, you see that the 2 ellipsoids that are placed along the x-axis have the longitudinal mass that is indicated with mu parallel, that is also associated to the x-axis. The longitudinal mass here is indicated with the symbol mu parallel because you remember the mobility is connected to the inverse, is proportional to the inverse of the mass. Okay, and the mass is the combination of the longitudinal and transverse mass. Okay, so if you have a different value of the mass, you have a different value of mobility. So here we have the indication of mobility instead of that of mass. In the direction normal to the x-axis, we have the transversal mass because it is the transversal axis of the ellipsoid and it is related to a mobility that is indicated with the symbol mu perpendicular. Okay. Now you remember that the transversal mass is smaller than the longitudinal mass, and mobility is proportional to the inverse of the longitudinal or transverse mass. So obviously the transverse mobility is larger than the longitudinal mobility. And you in fact see that the arrow is just symbolically chosen in order to indicate that the transversal mobility is large. If you look at the two ellipsoids that are associated with the y-axis, it is just the same, but all the situation is rotated. So the longitudinal mass is associated to a longitudinal mobility, and that is in the vertical direction. Instead, the transversal mass and the transversal mobility are in the lateral direction. Okay. So it is intuitive that if you apply a field in the vertical direction in this figure, you will find that the electrons that populate the two minima placed on the x-axis will react with the lateral mobility. Okay, so they will have a smaller mass and they will go, in quotes, faster. Okay. The electrons that are in the minima associated with the y-axis instead will react with the longitudinal mass, so they will be slower. The other two minima are not visible, but they are placed along an axis that is normal to the page. So obviously also these two minima will react with the transversal mass and the transversal mobility. Okay. Conclusion, the conduction will be a mixture of these effects because some of the electrons will react slowly, so to speak. And these are the longitudinal ones, those along the y-axis, and the other ones will react with a larger mobility. What happens now when we apply a stress? To first order, what happens is that the positions of the minima in energy will change. And this is intuitive because if you apply a mechanical stress, you deform the direct lattice. On the other hand, the reciprocal lattice is related to the direct lattice. So the characteristic vectors B1, B2, and B3 of the reciprocal lattice are calculated from the characteristic vectors A1, A2, A3 of the direct lattice. So if we deform the direct lattice, we also will deform, obviously, the reciprocal lattice. In so doing, we deform the Brillouin zone, so the dispersion relation will change. And the practical effect is that some of the minima of the conduction band, we are talking about silicon, will decrease. And some other minima will increase. In particular, those that will increase are those that are aligned with some components of the stress. And in this figure, we assume that the minima that decrease are those associated to the x direction. If the minima decrease, you remember the population of a minimum is connected with the distance with respect to the Fermi level. Assume that we are in equilibrium, okay? In a non-equilibrium condition, it is similar. So if the minimum goes down, it becomes closer to the Fermi level, so it is expected to be more populated, okay? Instead, if a minimum goes up, it will go farther away with respect to the Fermi level, and so it will become depopulated, okay? So this situation, this new situation produced by stress, is described by the dashed lines, the dashed contours, okay? You see here the dashed contours along the x direction are larger. Instead, those along the y direction are smaller. And they are not visible in the figure, but also those in the z direction will become larger, okay? In conclusion, what happens that by applying a stress, we have a population of the minima such that the conduction is dominated by the transverse mass, a population that is larger. So we have more electrons that are light, fewer and fewer electrons that are heavy, okay? So by this simple trick, we increase the mobility of the material, okay? Because instead of having an equal distribution of electrons spread over the 6 valleys, okay, and obtain a mixture of the mobilities, we privilege the electrons having a higher mobility, okay? This is in essence the piezoresistive effect in a material like silicon that shows that we can, within some limits, we can control mobility and consequently conductivity or resistivity of the material by mechanical stress, okay? If the mechanical stress is something that we want to measure, then the application is immediate. We measure a current, and this current will depend on the mechanical stress. Okay, so we can extract the information about the mechanical stress from the variation of the current or some other electric signal associated to the current. So it is a transducer from mechanical to electric, okay? This trick of increasing the conductivity is also used in technology. You may have heard about the silicon germanium devices, okay? So what are the silicon germanium devices? We have stressed at the beginning of this class that germanium should not be used because the gap of germanium is too small and the current density of a p-n junction in the reverse condition, that is the saturation current density, is too large, okay? So devices made of pure germanium are not efficient, but it is possible to place a layer of germanium on top of silicon by a process that is called epitaxy, such that the crystalline structure of the new layer of germanium is preserved. Why is it possible to connect germanium with silicon? You remember the lattice constant, that is the distance between atoms of the two materials, is similar. It's very close. They are very close to each other. So they are able to connect to each other and still form a crystal. But the difference in the lattice constant produces a mechanical stress. And if this mechanical stress is present, for instance, in an MOS transistor in the channel, and it is suitably oriented, then we can permanently improve the mobility of the electrons in the channel thanks to the effect that I have described a minute ago. Okay, so thanks to this effect, we can introduce some strain in the silicon lattice, and this strain enhances mobility. Okay, now let's come back to the present issue, the application of the piezoresistive effect to sensor. You see the formula here. We have that the electric field, in absence of any mechanical stress, is simply proportional to the current density and to the resistivity of the material, okay? And in the unperturbed situation, the resistivity is a scalar quantity, okay? When we have the mechanical stress, sigma, present in the material, then the situation changes, because as a whole, the coefficient connecting the electric field to the current density becomes a tensor, and the tensor has the form that you see here. In particular, the stress tensor is multiplied by another tensor that is indicated with the symbol capital Pi, okay, whose structure will be shown in the next slide. So essentially, this capital Pi produces a relative change of the resistivity of the material. Okay, so this is why it is indicated here as, you see the left-hand side, as delta rho over rho. Okay, it is the relative change in resistivity. Okay, the structure of the tensor is equal to that of the elastic tensor that we examined in the past lessons. Okay, we are considering silicon, so the elastic tensor and the piezoelectric tensor pi have only three independent components, and the structure of the tensor, as you can see here, is as usual. We have two blocks. One block is full 3 by 3, but there are only two independent elements, those on the diagonal pi 1, 1, and those out of the diagonal pi 1, 2. And the other block is purely diagonal with the third value pi 4, 4, and all the rest is equal to 0. We may, of course, split the formula that is at the beginning of this page in a component by component structure. So if we write it down in components and divide it by the coefficient rho e. Rho e in itself is a scalar. Okay, rho e is a scalar. The tensor is the quantity that is in brackets. Okay, so we have this type of relation that is fully general. So it considers any orientation of the field, and consequently we have the general formulas connecting the components of the field to those of the current density. But we may force one specific direction, okay? And in doing so, we can measure the components of the piezoelectric tensor one by one. It is very easy if you look at the left part of the figure. If you apply a force like F1 with the vertical alignment visible in the figure, and then you measure the voltage or the change in the voltage that appears when you apply the force with respect to the unperturbed situation. Obviously, if you look at the formula on top, in this case, you have that the only component of the stress tensor that has been applied is sigma 1,1. So all the other components of sigma are 0. Okay, so you have you measure the field by dividing the voltage by the length. The current is prescribed, okay, and the resistivity of the unperturbed case is given, so you measure pi 1,1. If you instead want to measure pi 1,2, what you do is simply that you apply a stress over phase number 2. So you have sigma 2,2 is different from 0, okay? Whereas sigma 1,1, sigma 3,3, and the mixed components are non-zero because you do not have shear forces. So in this case, you measure pi 1,2, and so on and so on. So by this, you reconstruct all the components of the piezoelectric tensor, okay? At this point, we must invent a method to exploit this phenomenon. A typical application of this effect is in sensors that must detect the formations of mechanical objects, okay? For instance, to measure weights or other forces, okay? So if you look, for instance, at this page, you see that the sensor is the small gray rectangle that is visible here in the left part of the figure or here, okay? The mechanical things whose deformation should be measured is the schematic profile, okay? Which is seen from top here or in the section here, okay? So you have a part of the mechanical piece that is thinner, is made thinner in order to detect to have a larger deformation of it under the application of forces. And then in the positions of the maximum stress over the surface of the mechanical object, we place the sensor. Okay, so the sensor can be aligned in the longitudinal or in the transverse direction. Okay, so we exploit one or the other terms of the piezoelectric tensor. Okay, or we can do even better. We do both. Okay, so we may place more than one sensor. Okay, and combine the information from these different sensors. So in the next page, sorry. Yeah. You see the typical appearance of a measuring system for mechanical deformations. If you look at the cross section, you have a piece of something. It's a mechanical piece that has been made thinner in order to obtain a diaphragm. Okay, something that is more easily bent. And assume, for instance, that you want to measure the difference in pressure from the upper side with respect to the lower side of the diaphragm. Okay. Then what you do is you place four sensitive elements on the diaphragm that are indicated with L1, L2, 3, and 4. And you see that L1 and R3 are aligned in a way that is normal to the edges of the diaphragm. And R2 and R4 are instead aligned parallel to the diaphragm. Okay. As you expect, under deformation, the voltage across these resistors will change. So of course these resistors are biased, so we can measure the change in the voltage of them. And the advantage of this placement of the sensor is that we can use a differential measurement. So if we connect these resistors by a Weston bridge, okay, we essentially, by the differential measurement, we eliminate the unperturbed part of the resistance. So if you look at this formula, okay, you see in the formula that the formula on top of the page that there is 1 plus pi times sigma. Okay, so if pi times sigma is small with respect to 1, of course you may have a noisy signal that is difficult to appreciate because you must detect the difference between the unperturbed and the perturbed condition, and this difference may be small. But with the differential measurement, you eliminate the unity here, okay, in the formula. So eventually, this unity will disappear and you are measuring only pi sigma. And this is visible if you look at this page, left bottom, you have that R1, R3 are equal to each other, and after the application of a mechanical stress, their common resistance will increase by some alpha 1 with respect to the value in the unperturbed case. Instead, due to the placement of R2 and R4, you see that the common value of the resistance will decrease by some factor alpha 2 with respect to the value of the unperturbed case. Okay, so when we calculate the differential voltage using the bridge, we eliminate the unity and we have just the combination of alpha 1 and alpha 2. Okay, so essentially this is the way in which we can exploit the piezoelectric effect for detecting mechanical deformation by transforming them into an electric signal. I will upload these pages. Here there is in the next some graphic representation about how to graphically identify the components of the piezoelectric stressor, but these are not important. And these are curves that represent instead the piezoresistance coefficient in terms of the concentration of the dopants and temperature for N silicon and P silicon. It is intuitive that if the dopant is very large, you see that the horizontal axis go from 10 to the 16th to 10 to the 20th, which is really, really large, okay? When you increase the dopant, the population of the electrons will increase very much so that the effect will be weaker and weaker, okay? It will be more and more difficult to make the populations of the minima of the conduction band unequal, okay? And the effect is also dependent on temperature, okay? And the reason intuitive is that the Fermi statistics will deform very much with temperature, so the populations again will change, okay? I don't know whether we have time. Yes. This is a picture of an actual transducer. So the diaphragm is in the left part of the figure is the dashed, the boundary of the diaphragm is the dashed line. In the right part of the figure it is, sorry, better visible. Okay. The piezoresistors are placed not exactly as I indicated in the other figure. The placement is a little bit more different, okay? They are placed on the side, but the result is the same. So this is called by Motorola is a transducer piezoresistor. And then, of course, there are the circuits around that detect the signal and provide the information about the deformation of the diaphragm. So I think this is the last figure of this series. Let me check. Yes, so we must take it out. And it's better that we stop here because we have completed the subject. Okay, so we will start at 10:10 with another subject. So we take the intermission now. If there are questions, there are still 3 minutes left, so you may ask or drop a message with some question. Okay, so we'll start. Let me share the screen. You should now be able to see a figure showing the elementary block of material. And you may remember that when we started discussing the problems of elasticity, we left behind two things. One thing was that at some point we started considering only the equilibrium condition of the elementary block. That is the situation in which all forces and all torques or moments balance each other. But we said we also have a dynamic condition that for a while we have neglected. We should consider this again just to show that the general equation of elasticity for the macroscopic bodies that is derived from the consideration of the dynamics of the microscopic bodies eventually is identical to the equation that we derived earlier from the consideration of the microscopic situation, so starting from the atoms. Okay, so eventually the two equations starting from macroscopic or microscopic will coincide with each other. The second point that we left behind and that we are now going to consider first is the analysis of the moments, okay? Because at some point we said the analysis of the equilibrium of the moments that we carried out last week seems to work only if the elementary block is cubic. But this, of course, is nonsense. It should work in all situations, even if the elementary block is non-cubic. So we have to show this now. And so we remember that the sides of the elementary block are A1 in the direction x1, A2 and A3 in the other two directions. And now we assume that these A1, A2, A3 are different from each other. And we impose the balance of the stresses in this condition. Okay, so we start considering the two opposite faces normal to axis x1. And we consider the stress as the force per unit area acting on these two faces. So for the moment we start considering vectors. So the vector sigma 1 plus is the force per unit area that acts on face normal to axis 1 and on the positive side. And sigma 1 minus is the analog on the negative side of the elementary block, okay? And then we indicate with scalars, as we did earlier, the projections. So they are sigma 1, 1, 1, 2, and 1, 3, but they keep the apex plus or minus, okay? Then you remember that we call the normal stresses those whose indices are equal to each other, and shearing stresses those whose indices are different, okay? What are these forces? As usual, these forces are those that are exerted upon the block that we are considering by the remaining part of the body. So we have a much bigger body, we have removed all the other parts and left only the elementary block, okay? So the components on the positive face are found by projecting vector S1 plus with respect to the unit vectors of the axis, okay? Because we have three components of sigma 1 plus. Those on the other side are found by considering the projection with respect to the negative unit vectors, okay? Now we consider the equilibrium condition, and we impose an equilibrium condition globally, so using directly the vectors, okay? So the two vectors of stress of the type sigma 1, that is those acting on the faces that are normal to axis x1, globally produce a force per unit area, that is this parenthesis here, sigma 1 plus plus sigma 1 minus, times the area of the face. This is where the extensions of the sides of the block come into play, okay? So the area of the face is A2 times A3. Next, if we call sigma 2 plus or minus the stress vectors related to the faces normal to axis x2, then globally their action multiplies the area A3, A1, and similarly for the remaining other two stress vectors, we have the area A1, A2. So globally, this is the total action on the block. This must be zero, but this must be zero also for any arbitrary choice of the areas of the sides. So for instance, that expression must vanish even if we double A2 without touching A1 or A3, or similarly. Okay, so it must be true for any choice of the lengths of the sides of the block. So in conclusion, we have that sigma I plus is equal to minus sigma I minus, okay? Which means that the components are equal to each other, because you remember the projections are made with respect to either the positive unit vectors or the negative unit vectors. Okay, so the vectors differ by the sign, by the projection don't. And this is the first relation. Okay, so we have a unique value of the stress Sij. We should not distinguish anymore the plus and the minus type. Okay. Now we consider the moments. Okay. Now the moments must consider at the same time the distance of the shear components of the stress tensor with respect to the center of the block, and the area of the face to which the shear components are applied. So consider the shear component of the type 2,3. It must be multiplied by the area of the face normal to axis A2. So sigma 2,3 must be multiplied by A3, A1, and then the moment is calculated by multiplying the force times the distance with respect to the center, and this is A2 divided by 2. In order not to have a rotation of the block, this moment must be equal to the moment exerted by the opposite from the opposite phase, and this is sigma 3,2, okay, times the area of the face, that in this case is A1, A2, times the distance of the force of the point of application of the force with respect to the center, okay? So by this equation, you see that all the coefficients cancel each other. And we obtain that sigma 2,3 is equal to sigma 3,2. So the tensor is symmetric, okay? So this is the correct demonstration involving also the surface areas of the faces of the block. But they eventually in the calculation cancel, okay? So the symmetry of the tensor exists also if the block is not cubic. So this solves the first aspect that we had left behind. So the correct calculation of the balance of the moments. Now assume that there is no equilibrium. Okay, there is no equilibrium. That means that the forces acting on the different faces are different, so the block is accelerating because globally the force and moment applied to it are non-zero. They are not balanced exactly, okay? That means that if we consider, as we did before, the two components of the tensor on opposite faces, they must be different. So sigma, if we consider the face normal to axis 1, the component sigma 1j, j goes from 1 to 3, so we are including in this both the normal and the shear components of the tensor. Sigma 1j minus is different from sigma 1j plus, okay, if there is no equilibrium. Sigma 1j minus will be called sigma 1j. Sigma 1j plus, due to the smallness of the cube, because the sides of the cube are very small, can be expressed using a first order expansion with respect to the sigma minus on the other side. So what we have is that sigma 1j plus is equal to sigma 1j minus, that is sigma 1j, plus, since we are considering axis 1, we must consider the derivative of sigma 1j with respect to x1, the first coordinate, and then we multiply by the distance from the two faces, that is a1, okay? So we have an unbalanced force. If we want to calculate this force, we must take the difference in the two values of the stress, and then we multiply it by the area of the face normal to axis x1. So the global force incorporating all components, because J ranges between 1 and 3, okay? The total force is the difference between sigma plus and sigma minus times the area of the phase. So the global force is the derivative of sigma 1j with respect to x1 times the volume A1, A2, A3 of the elementary block. Obviously, we can repeat the analysis for the phases 2 and 3, and then we add up the contributions. Okay, so in essence, we have that the sum of the derivatives of sigma wj with respect to xw times the volume is the global force acting on the elementary block. At this point, we remember that the stress tensor is symmetric, so it is preferable to exchange the two indices and call this derivative of sigma jw, as you can see, instead of wj, with respect to xw times the volume. Okay, so this is the force acting on the elementary block in a non-equilibrium condition. Okay, obviously this force is not a vector, it is component by component. So J is the index of the component of the force. On the other hand, the component of the force must be equal to the mass times the component of the acceleration. Okay, so what is the component of the acceleration? Is equal to the total mass of the elementary block that we call m. Then if you remember, we expressed the position of the block with the symbol psi. So the mass times the second derivative of psi j with respect to time is the force, because it is the mass times the acceleration, component by component. On the other hand, what is the mass? The mass is the density of the material, ρ, times the volume of the elementary block. So at this point, we have that the force can be written as ρ times A1, A2, A3 times the second derivative of psi j with respect to time. This must, of course, be equal to the expression in the first line. So when we make them equal, we can eliminate the volume. So the product A1, A2, A3 cancels down. And what we obtain is the density times the second derivative of the displacement of the block. So the second derivative of the displacement of the block with respect to the coordinate j is equal to the sum of the derivatives of the components of the stress tensor with respect to the coordinate. Essentially, it is the divergence of the stress tensor. Okay. Now, if you look at this formula, you find out that this formula is identical to the elasticity law that we derived starting from the elementary description of the atoms. You remember we had the elementary cell. We consider the acoustic modes with large wavelength, so that all atoms of the single cell would move in unison. With several steps, we derived an equation that was the elasticity law of the continuous medium, and that is identical to the expression that you see here. Okay, so this comes from macroscopic consideration, the other one from microscopic consideration, and eventually they are consistent with each other. We have another consideration necessary about the stress tensor sigma, and the consideration is the following. We have a 3x3 tensor that we can express in matrix form, okay? And using this matrix, we can build up an eigenvalue system, okay? We say we multiply the stress tensor by a vector and impose that the result is a scalar quantity, that is a number times the same vector. So we want to build up an eigenvalue problem based on the stress tensor and see what happens when we do this. Okay, so it can be demonstrated that solving the eigenvalue problem for the stress tensor is equivalent to solving this problem. The eigenvalue problem is a transformation of the linear form. Okay, so we can use, as you remember, we did it in another occasion on the crystal. We can use the eigenvalues to form another matrix, and this other matrix can be applied to the reference. Okay, so it is used as a linear combination of the elements of the reference. This is equivalent in this case here to a rotation of the reference. Okay, so we simply take, it is like we take the elementary block and then we find a rotation that rotates the elementary block, aligning it with the new reference in which the unit vectors are the normalized eigenvectors of the problem. Okay. In the new reference, the stress tensor will be different. Okay, because we go from the old reference to the new reference by a linear combination as usual. Okay. So it can be demonstrated that in the new reference, the normal components of the new stress tensor are stationary. So they are maximum or minimum. Okay, so the eigenvalue problem is equivalent to find a new reference in which the normal components of the stress tensor, that is those that are on the diagonal, are either maximum or minimum. Okay. Here the components of the eigenvectors will be called B. Okay, and we force the condition that the eigenvectors have a length equal to 1 and they are orthogonal to each other. Okay, so this product is made of the components of the eigenvectors. So 1, 2, and 3 are the components of the eigenvectors. U is the counter of the eigenvectors, because this is a 3 by 3 problem, and we expect to have 3 different eigenvectors. Okay, so these eigenvectors must have the modulus equal to 1. Okay, and they must be normal to each other. Okay, so the scalar products of the three eigenvectors must be 0. Now we jump to the eigenvalue system. Okay, so this is the eigenvalue problem written as a system of three equations, linear equations in the unknowns, and the unknowns are the components B of the eigenvectors. Okay, so sigma is prescribed, is the stress tensor in the original reference. B1, 2, and 3 are the components of the eigenvectors, and sigma prime, U is the eigenvalue. Okay. This symbol sigma prime is inconvenient, so of course we have a 3 by 3 system, so we expect that there will be 3 eigenvalues. It is more convenient to call them S1, S2, and S3. Also, without solving the problem, we know that the eigen values will have some properties. For instance, since the strain tensor is symmetric, then we expect that the eigenvalues will be real. Okay, so these three numbers S1, S2, S3 are real. On the other hand, the algebraic system as a whole has real coefficients because sigma is real, the eigenvalues are real, so we can conclude that also the eigenvectors will be real. Okay, so we have a set of real eigenvalues and real eigenvectors, and the eigenvectors will be normal to each other and normalized to unity, which is very easy because the system is homogeneous. Okay, how do we find? Oh, by the way, you remember when you solve an eigenvalue equation, the first thing that you find is the eigenvalues themselves. Okay, and we expect to have 3 of them because the system has a dimension of 3. Then we take eigenvalue number 1, S1, place it into the system so that we can find the eigenvector associated to it. So one of the B's, okay? We call it Ni1. So Ni1 is the eigenvector associated to eigenvalue S1, this non-trivial solution of the system produced by the first eigenvector. And similarly, we find the eigenvectors Ni2 and Ni3 by inserting one after the other S2 and S3 into the system. And these eigenvectors are mutually orthogonal and normalized to 1. Okay. How do we find the eigenvectors? Of course, we do it by solving this algebraic equation that is derived by imposing that the determinant of this determinant is equal to 0. So it produces an algebraic equation of the third degree. In this context, this algebraic equation is called the secular equation. Okay, the term is due to Laplace because he was studying this type of equation in investigation on planetary motions. Okay, so it is called secular. Now assume that we have done all the calculations so that we have found the new system produced by the eigenvectors Ni1, Ni2, and Ni3, okay? And by the other considerations, we know that the eigenvalues S1, S2, S3 are either maxima or minima. What does it mean? It means that if we start from the situation associated to the new reference, Ni1, Ni2, and Ni3, and you rotate it by an infinitesimal rotation, of course, S1, S2, and S3 will change because there is a rotation, but they will change by higher order variation, okay? And this is typical of being in a minimum or in a maximum, okay? The question is, how do the non-diagonal elements of the tensor, of the original tensor transform, okay? We now know that the diagonal in the new reference have a maximum or a minimum, okay? What happens to the non-diagonal terms? Well, after obtaining the transformation, we simply calculate the transformed values of the non-diagonal components, okay? So this can be done by a bilinear transformation, okay? I'm not going through the details, but the bilinear transformation is this, okay? So let's call sigma prime of UW with U and W different from each other, the value of the non-diagonal terms of the stress tensor after the rotation, after the transformation from the original reference to the reference Ni1, Ni2, Ni3, okay? It can be demonstrated that the new elements can be found from the old elements by this sum. So we have a double sum over all terms sigma ij of the original tensor times the components new ui, new wj of the unit vectors in the new reference, okay? This sum can be manipulated, okay, because you can extract this piece because this piece contains u and u does not appear anywhere else, and then it is still interior to the sum over index I. And then you have the internal sum, and the internal sum is over j from 1 to 3 of sigma ij nu wj. Now you can compare this sum with the original eigenvalue problem, okay? And you see that this sum is exactly this sum here, okay? Here the eigenvectors are called with the symbol b, but they are the same as symbol nu, okay? So each line can be replaced with this line, okay? With this term. So we do it. So this sum over J becomes the eigenvalue SU times Ni Wi. Okay. On the other hand, the eigenvalue SU does not depend on index I, so we can extract it. And what we are left with is the sum of component by component of the products of the component of the eigenvector of index U times the eigenvector of index W. You remember that we are seeking for the expression of the non-diagonal terms of sigma prime. So U and W are different. So Ni U and Ni W are two different unit vectors associated to two different axes. So they are, of course, orthogonal to each other. And this sum is nothing else than the scalar product of the two. So this sum is 0. And this is a very important conclusion. When we calculate the eigenvectors and the eigenvalues of the stress tensor, and then we rotate the reference in order to adapt it to the new eigenvectors, in the new reference, not only the diagonal terms of the stress tensor are maximal or minimal, but the non-diagonal components are 0. So in this case, the stress tensor is diagonal. And the tangential stress or the shear stress in the new orientation of the block is absent. Okay? So the new directions that we have found associated to the unit vectors Ni1, Ni2, and Ni3 are very important. In fact, they are called the principal axis, and the components SU, that are the eigenvalues, are called the principal stresses. Okay? And if we take the principal axis 2 by 2, they define 3 planes that are called the principal planes. Okay? Why is this result important from the practical view or standpoint? Okay. Well, you know, in constructions of buildings, for instance, or any structure, they use reinforced concrete. And reinforced concrete is concrete in which they insert metal bars. Okay, metal bars can only resist normal stress, of course. Okay, you can only pull a metal bar. Okay, it resists well if it is pulled, otherwise it does not. Okay, so the fundamental question for the people that design structures in civil engineering is, where should we place the metal bar? And the obvious answer is the metal bar should be placed in the direction of the principal stresses. Okay? Because when you have found the direction of the principal stresses in the structure, you know that there are no shear, no tangential forces. Okay? Because there are only the principal stresses in that situation. Okay? And if you place the metal bars aligned with the principal stresses, of course, they will be pulled and the structure will not collapse. Okay, so this is very important from a practical standpoint. Okay. There is some nomenclature here. It may happen that the eigenvalues are different. Okay, So if that happens, of course, you have three different solutions to the problem. And when you insert one by one the eigenvalues in the system, you find three eigenvectors, and they will be different from each other because you inserted three different values of the eigenvalues, okay? There are situations in which maybe two eigenvalues are equal to each other and the other one is different, okay? So the different one will give you one well-defined eigenvector, okay? The other two will give you the possibility of selecting a plane normal to the first eigenvector, and then over this plane, any pair of vectors ni2 and ni3 that are mutually orthogonal will do as unit vectors, okay? So you have an infinity of possible principal references, okay, with one axis given and the other two axes anywhere in the plane. The last possible outcome is that all eigenvalues are equal, and in that case, any orthogonal reference is principal. So this is an easy problem, okay? Still, other possibilities are that if the eigenvalues are all different from zero, the stress condition of the material is called triaxial. If only two eigenvalues different from zero, the stress condition is called biaxial or planar, okay? And if only one eigenvalue differs from zero, the stress condition is called uniaxial, okay? Of course, it is impossible that all eigenvalues are zero, okay? So this completes the aspects related to elasticity. We have a few minutes left, but they are enough to introduce another subject, that is the heat equation, okay? So we now turn from the analysis of mechanical sensors to the analysis of sensors devoted to the detection of temperature, okay? The heat equation has similarities with the diffusion equation. Actually, the structure of the heat equation is exactly that of a diffusion equation. The heat equation is an equation that is also called the Fourier equation, and it was enunciated by Fourier, of course, in 1822, okay? So the symbols that are used in this page, I am not sure whether you see it, but let me share the screen. Okay. So we call T temperature, okay? And then we indicate the heat flow with the vector C, okay? You know that heat can be transported in different ways, okay, that are traditionally indicated as conduction, convection, or irradiation, okay? Here we are talking about conduction. Conduction of heat is what you obtain if you have, for instance, a metal bar. You make it hot on one end and you see that there will be energy in the form of heat flowing across the bar, okay? With no motion of matter, okay? There is no fluid that moves in this type of transport of heat. So the heat transport equation related to conduction has the form of the diffusive type, as you can see. That is, the heat flow C is proportional with the minus to the gradient of temperature, okay? And the coefficient is called the thermal conductivity of the medium, okay? So it is quite similar to the diffusion type equation, in which instead of K you have diffusivity of the particle that diffuse, okay? Then if you indicate the density of the medium with rho, and then you indicate the specific heat, we shall come back to the specific heat in the next hour, okay? And we call it small c. Then we can combine the continuity equation for the heat. As you can see in the line, it is C rho derivative of T with respect to time plus the divergence of C equal to 0. You may understand the meaning of this equation by inserting, assume that C and rho are constants, they typically are, okay? And put them near the temperature, okay? So the specific heat times the density times the temperature will give you the heat per unit volume under the time derivative, okay? So it is like the time derivative of the heat per unit volume plus the divergence of the flux equal to 0, which is the typical form of the continuity equation, okay? Now we can combine this equation with the heat transport equation of the conduction type. So we replace C with minus K gradient of T, sorry, kappa gradient of T. We assume that the thermal conductivity kappa does not depend on the coordinates. So we take it out of the operator. Divergence of gradient gives you the Laplacian. We bring it to the other side. So the minus sign becomes a plus. And finally, we have coefficients. And these coefficients are grouped together as kappa over C times rho, okay? And one easily finds that D has the units of an area per unit time, okay? So it has the same units as the standard diffusion coefficient, and we call it the diffusion coefficient for heat, okay? So the equation that is visible as equation 1190 is the equation for the heat, or the Fourier equation, and has exactly the same structure as a diffusion equation, and it can be solved by similar method as the diffusion equation. Okay, so now we stop, and we shall start again in 10 minutes.
Live for nothing or die for something.
Okay, there was some problem with the connection, but now I think it works. So we restart, and briefly I want to illustrate how to solve the diffusion equation. You remember from the previous hour that the diffusion equation is a very general equation that applies to the diffusion of heat. In this case, it is called the Fourier equation, or also applies to the diffusion of fluids or other substances. Assume that the diffusion coefficient is a constant. So, and assume that you want to solve the diffusion equation in one dimension. The solution in 2 or 3 dimensions is identical because the equation is separable. So we can simply find the solution in one dimension and then replicate the analysis in the second and third dimension. And the other property of the equation is that the equation is linear. So we can solve it by separation, by separating the time with respect to the coordinates, okay? Now, a general method for obtaining the separation is using the Fourier transform. So we start from the assumption that the function that represents the solution of the heat equation can be transformed with respect to the Fourier transform. That is, the modulus of the function is integrable. So in this slide, the unknown is small f, and it depends on position and time. So we assume that the absolute value of f is integrable. That means that f goes to 0 at infinity. Then we define the Fourier transform of small f, we call it capital G. And this transform is with respect to x. So the second line shows that G depends on omega, but omega is not a frequency. It is not the inverse of the time, it is a spatial frequency. So it is in the inverse of space. Omega has the units of the inverse of x. So we calculate the Fourier transform by multiply f by the exponential of minus j omega x and then integrating over x. The result is G. G depends on t, of course, and on parameter omega that appears in the transformation. The inverse transform, as you may well remember, is obtained by taking G, multiplying by exponential of j omega x and integrating over omega, and finally dividing by 2 pi. What is the important property of the Fourier transform? The Fourier transform can be applied also to the derivative of f, and if you do it, you can perform an integration by parts. That's very easy. What you find is written in this line here. That is, the Fourier transform of the derivative of f with respect to x is like the Fourier transform of f times j omega. That is, times the exponent of the exponential. If you take the second derivative, so if you transform the second derivative, you have j omega squared. Or more generally, if you transform the nth derivative, you have j omega to the nth power times the Fourier transform of the original function. So this is the important issue. It tells you that if you have a linear combination of derivatives of a function, and then you Fourier transform this linear combination of derivatives, what you get is a linear combination of j omega. So you transform by this method a differential equation into an algebraic equation. You turn a differential equation into a polynomial, okay, which is in general much easier to solve than the differential equation. Then you solve the polynomial and then you go back by anti-transforming. And so you recover the original function, okay? For the equation of the diffusion type, this is quite easy, as we shall see in a minute. I don't think we need these definitions. We just need an auxiliary function. The auxiliary function that is necessary for us to proceed is called capital delta. And it depends on two space coordinates, x and psi, in the difference. And then it depends on time. And the definition of this delta is the exponential of minus x minus psi squared divided by 4 times the diffusion coefficient by t, divided by the square root of 4 pi dt. Okay, so in here, the coefficient d is the diffusion coefficient that will eventually appear in the diffusion equation, okay? Here is just a parameter whose units are those of a diffusion coefficient, okay? X is the space variable and psi is another auxiliary space variable. What are the properties of this function? One property is that its integral over psi is equal to 1. And another important property is that it is possible to represent this function delta with an integral. And in particular, the integral is written here. It is 1 over 2 pi. Integral between minus infinity and plus infinity of the exponential of j x minus psi omega minus dt omega squared, all integrated with respect to omega. How come that this integral is equal to this function delta? Well, this can be proven by manipulating a little bit the exponent, okay? You see, the exponent depends on omega, whereas time, x and psi are parameters, okay? They're fixed during the integration. So we can compact these parameters into two coefficients we call small a is equal to jx minus psi, and small b is equal to d diffusion coefficient times t, okay? So the exponent becomes A omega minus B omega squared. And this difference can be identically expressed in another form that is more convenient. It is A squared over 4B, that is a constant with respect to omega. It does not depend on omega. Minus B, parentheses, omega minus A over 2B squared. Okay? So if you replace the latter form of the exponential into the integral, of course, the piece having A squared over 4B in the exponent is extracted from the integral. And what is left is minus B times omega minus A over 2B squared. So now we have to integrate we have to integrate the exponential of minus B omega minus A over 2B squared. And for this, we go back and we exploit properties of special functions, okay? The only thing that is necessary for you to calculate that integral is that the integral of exponential of minus x squared from 0 to infinity is square root of pi over 2. And that the same applies to the integral from minus infinity to 0. Okay, these are very well-known results of calculus. And the integral between minus infinity and plus infinity is just square root of pi without the division by 2, okay? So the issue is, I'm not going through the calculations, the issue is if one replaces this form of the exponent into this and change the variables, we'll immediately find that the result is the function delta. Okay, it's just a simple algebraic manipulation. You should change the variable in the integral and you find this result. Okay, so we now remember this function, and we also remember that this function is expressible with an integral. Okay, now we solve the diffusion equation. You remember in the other slides, the unknown function was the temperature T, but the form of the equation is just the same. So this is the one-dimensional form of the diffusion equation for some variable that we call capital N. When it comes to the heat equation, then N is the temperature. Okay? Since we are considering an equation with the derivative with respect to time, it is necessary to know the initial condition. So we assume that we know the initial condition. And this initial condition is simply the unknown function n for every x at t equal to 0. And this function is called n0 of x. In the example of the heat flow through a metal bar, in which we have that one end of the metal bar is brought to some temperature, okay, and we want to calculate the diffusion of heat through the bar. the initial condition would be that initially the bar is at room temperature, and this temperature is the same at each position of the bar at t equal to 0. Then we simply perform the Fourier transform of the equation. So we call capital G is the Fourier transform of n. Capital G0 is the Fourier transform of n0. Okay, so it is like G at t equal to 0. Then we transform the left-hand side of the equation. So the Fourier transform of the time derivative of n, you remember this Fourier transform is with respect to x, so it is an integral over x. And this integral can be exchanged with the derivative with respect to time. So it comes about to be the time derivative of g. Next, we have to calculate the Fourier transform of the right-hand side of the equation. D is a constant with respect to space, so we extract d from the integral, and then we take the transform of the second derivative. But you remember the transform of the second derivative is j omega squared, that is minus omega squared, times the Fourier transform of n, that is g. So this is the Fourier transform of the second derivative. When we put these two results together, we have an equation with respect to time only, that is derivative of g with respect to time is equal to minus omega squared diffusion coefficient times g. Okay, we integrate immediately this equation because it is first order equation. It gives us that the logarithm of g over g0 is, consider that d is constant with respect to time, okay? So don't worry about this integral, okay? And assume that dm is equal to d. So when we integrate minus omega squared d with respect to time, we simply obtain minus omega squared d, that is a set of constants, times t, okay? It follows that g is equal to g0 times the exponential of minus omega squared dt. Okay, so we now have g. Since we have g, we can find n by anti-transforming. So n is the inverse transform of g, that is 1 over 2 pi. You remember g is g0 exponential of minus omega squared dmt times the exponential of j omega x. We're almost done. Now what we have to do is remember what is g0, but g0 is the Fourier transform of n0, so it is given. It is a known function, okay? But it is important now to express here g0 as a Fourier transform. So g0 will be the integral of n0 times the exponential of minus omega. It should be omega x, but we must be careful because x is already in this integral, okay? So we cannot express g0 as an integral over x, because in this way we would mix the two x variables and then we would make confusion. So we must express G as the Fourier transform using a different symbol for the variable. So we use psi. So we have m0 of psi exponential of minus j omega psi. Then we group the exponentials together and we have this double integral over psi and omega of n0 exponential of j omega x minus psi minus omega squared dmt. And you see immediately that you have the function that we discussed before, because we have this exponential integrated over omega. So we have exactly this expression here. And we can easily separate the two integrals because the other factor in the double integral is n0, and n0 does not depend on omega. So what we do is we extract n0 from the integral over omega. We put it in the middle of the two integral signs here. We integrate this over omega and we get delta. Okay. Conclusion, we have found the solution of the equation. You see the unknown function nx of t is expressed as an integral of n0, but n0 is given because it is the initial condition. So n0 is prescribed. And delta is given because it is, remember, the exponential of minus x over psi squared divided by 4 dt divided by the square root of 4 pi dt. Okay, so delta is given. The conclusion is that the solution of the diffusion equation can be expressed as a convolution integral of the initial condition times a special function. Okay, so this is a very general and very powerful result. It can be extended also to even more general situations. For instance, it can be extended to the case in which there is some variable that depends on time. For instance, if you are producing heat somewhere inside the bar by attaching a heat source, okay, this equation can be generalized relatively easily to other cases, okay? So before we proceed, I just want to show an interesting application of the diffusion equation to a case in which there is a boundary condition that is oscillating, okay? So let me change okay, this example is not part of the exam, it's just a curiosity. Consider a situation in which you have solved the heat equation in one dimension for a situation in which the boundary condition is at the position x equal to 0. So if you look at the horizontal axis, the horizontal axis is the position x normalized to some quantity x0. Okay? And the boundary condition is at x equal to 0, so it is on the left. And this boundary condition is the temperature, and the temperature oscillates with respect to time. And here it is expressed in degrees centigrade, okay? So assume that this is the temperature at ground level in some point of Earth in which in summer the temperature may become very hot, like 40 degrees, okay? And in winter, it may go down to -10, okay? So this is the oscillation of the temperature over 6 months. So maybe the black line, 40 degrees, is like July, and the blue line is maybe January, and the other lines are intermediate months, okay? So the black dashed line is, I don't know, maybe it's September or so, okay? And these lines show the temperature inside the ground, okay? When you go deeper and deeper and deeper, into the ground, starting from the ground level. And in this case, the diffusion coefficient of the equation is the diffusion coefficient of heat through soil, okay? And the diffusion coefficient of heat through soil is written, is here, is 2 times 10 to the -7th here square meters over second, okay? So you find that the temperature oscillates at the surface, and also when you go inside Earth, the temperature oscillates, because when time changes, okay? But you see the interesting result that at some depth, for instance, here at corresponding to 2.5, the blue line that corresponds to the temperature of winter is positive. And the black line that corresponds to the boundary condition of summer is negative. Why is it so? Because the diffusion coefficient of heat through soil is so poor, is so small, that the flow of temperature can take months to propagate inside the Earth. Okay, so it is in counter phase at some depth with respect to the surface. If you also consider what happens about 3.5 or 4, okay, you see that the oscillation of temperature at some depth is a few percent with respect to the oscillation at the surface. So if you go deeper into the soil, you don't feel that much the variation of temperature. The temperature is about 15 centigrades all over the year, okay? If you consider the depth at which this happens at about 4 meters in the underground, okay? 4.45 meters, okay? This is the reason why cellars for storing food are typically at 4 to 5 meters in the underground, because the temperature stabilizes to a few percent fluctuation with respect to that of the surface, irrespective of the fluctuations at the surface, and also the temperature is in the counterphase situation with respect to the surface. So it is a little bit cooler in summer and hotter or warmer in winter, okay? So this is an interesting application. It's not part of the exam, but it's a curiosity. Okay, so now I have to change the slides. Okay, so now you should be able to see slides from Professor Reggiani that synthesize some of the issues that we will consider to complete this lesson today and in the next lesson. What are in general thermal sensors? We may have different types of processes, like you may have a signal that you want to detect that is not necessarily thermal at the beginning. It may be something else, but it is easily transformed into heat power, okay? And the heat power is used to force a difference in temperature of some device. And finally, the difference in temperature of the device is transduced into an electrical signal that is easily detectable, okay? So for this, we shall see we are using the so-called thermoelectric or thermoresistive effects. Here there are some symbols. Here V is a volume. So if capital Q indicates a form of energy in the form of heat, then small q is heat per unit volume, okay? And do you remember we already examined a continuity equation for heat, and we had with different symbols, we had the time variation of the heat per unit volume. Actually, there should be the partial derivatives with respect to time, not the standard derivatives, plus the divergence of the heat flux that was indicated with capital C in the other collection of slides, okay? As usual, if you do not have any source or sink of heat, in this case, you have a zero at the right hand side. But if you have a heat source, then you have to introduce it, okay? So P source is the heat that is generated per unit volume, okay? Or you may also have a heat sink, okay? That is something that absorbs heat instead of generating heat per unit volume. It's like when you have generations and recombinations in semiconductor, the concepts are just the same, okay? The physical quantities are different. As I said before, there are three mechanisms for transferring heat. One is conduction, okay? Here it is mentioned that heat conduction occurs across a boundary, but it is not necessary that there are two bodies in contact. I mean, you have conduction also inside the same body. You have the example of the metal bar that we made before, okay? You may have heat transfer because one end is kept hot and the other end is kept cool, okay? Then you have convection. Convection is a type of conduction of heat in which you have a fluid that moves, like in the heating systems in houses, okay? Or also in the car engines for keeping the engine at the same temperature, okay? And then you have irradiation, that is the emission or absorption of electromagnetic radiation, and of course that radiation carries energy. So we already met the Fourier law. In the previous slides, the heat flux was called capital C. And here K is the original, kappa is the thermal conductivity. A simplified model for convection is that heat flux is proportional. Delta is not the Laplacian. Delta is just the difference, okay? The difference of temperature between one body and another, okay? And alpha is called the convective coefficient. And then there is radiation. In this case, the heat flux, we already met this expression when we consider the solar cell, because we had to calculate the solar constant. You may remember this. So the heat flux in the case of irradiation is given by the Stefan-Boltzmann equation, in which epsilon t is the emissivity of the body, that is equal to 1 for the black body. In fact, you remember we did not use the emissivity when calculating the solar constant, because the sun can be considered to a good approximation as a black body. For other bodies, of course, you need it. Other important concepts are the heat capacity, that is the variation of the heat that is transferred with respect to the variation of temperature. Heat capacity per unit volume is simply the above divided by the volume. So it is d small q over dt. And the specific heat is the heat capacity per unit mass. Obviously, the relation between heat capacity and specific heat is that specific heat times density makes the heat capacity. Actually, one should distinguish between heat capacity at constant volume or heat capacity at constant pressure, because they are different from each other. They are important when you consider, for instance, gases, you remember, because when you heat a gas, it tends to expand, okay? So we must distinguish between the two heat capacitances. In this case, it is not relevant. And we have the heat flow equation, again, that we already discussed earlier. Here we have a difference that there is also a source of heat. So when we renormalize the equation to go from the heat per unit volume to temperature, okay, we have to divide the heat produced by the source per unit volume. We have to divide it by the product of the density and the specific heat, okay? So this is the Fourier equation with an additional term that depends on the of a source, okay? If we do not have the source, the distribution of temperature inside the body is prescribed only by the boundary conditions, of course, and by the diffusion coefficient. If we have a source, we have another additional term that can be incorporated easily into the solution of the heat equation that we examined before. There are similarities between electric and thermal equations. I think there are some misprints on this page, so I must fix them. So I will upload the correct version of it. We can proceed with the analogies between electrical and thermal phenomena by observing that if we multiply the heat capacity per unit volume, that is rho C, by a volume of the body, we obtain the thermal capacitance of the body. Similarly, we can define a thermal resistance of a body in a manner that is absolutely identical to the definition of the electrical resistance of the body. That is, you remember, for the electrical resistance, we say the electrical resistance is equal to the length, if you consider a bar, okay, of the length of the bar divided by the cross-sectional area A of the bar multiplied by the resistivity, which is equivalent to divided by the conductivity in the electrical case. In the thermal case, you divide by K, that is the thermal conductivity. Okay. At this point, you may manipulate the differential equation as we do by going, when we go from the microscopic description of an electrical device to the concentrated element circuits, okay? When we go to devices from circuit, in circuit we used essentially generators, resistances, capacitances, and inductances, okay? We can do the same if necessary for thermal circuits, and we obtain the equation that is below in this page, in which we are using macroscopic quantities. So P source is the total heat produced by the source, and we have a differential equation with respect to time only, in which the thermal capacitance and the thermal resistance appear. Like in the case of electric quantities, you remember a resistance times a capacitance is a time, okay? That is called tau. In this case, a thermal resistance times a thermal capacitance is also a time. We simply replace the definitions, and we of course have to remember that the product L times A is the volume, okay, and we obtain that thermal resistance times thermal capacitance is also a time. I think there is no time left. The next subject will be the application of this concept in order to obtain sensors, okay, thermal sensors. And the first example will be given by the application of the p-n junction for detecting changes in temperature, okay? So for the moment we stop, and we shall meet again on Thursday, okay? So for the moment, I thank you for the attention. If there are questions, there is still 1 minute left.